for coming, because I know this is the only thing standing between you and a long vacation. So it's very kind of you. All right, so I'm going to be speaking about classical and free zero bias for infinite divisibility, and the basis or kind of the foundation of this work and some other work that I do is based on what are called, I'd say, distributional transformations with fixed points that are motivated by Stein's method. And so the idea, these distributional transformations have had, I think, a good amount of success in first in probability and then stochastic analysis and lately in statistics as well. So I've been curious for a long time whether these distributional transformations also can be applied, if they even exist, in these other realms of probability, particularly the one that's known as free probability. But first I'm going to do kind of half the talk will be on some work that I've done. This is joint work with first with Uwe Schmuck, who's in Vienna, and this is the classical portion. And then I've been working with Todd Kemp at UCSD and extending some of this some of these ideas into this world of so-called free probability. Okay, so we'll start with the classical version. Here's a game of telephone, and I'm going to be speaking about various kinds, as I say, transformations, and one of them is based on biasing, size biasing in particular. So you may recall before you had cell phones, right? People actually had lines with wires that came into the house, and the particular house may have had various lines coming in, right? You could have, right, the parents wanted to speak on the phone, and the kids would always hog the phone, and so the parents might buy another line for the kids, and then there's a fax line, et cetera. And so maybe if you're a statistician and you wanted to know the average, average number of phone lines per household, then you'd have a brilliant idea. You'd say, I'm going to call a number at random digit dialing. It's completely unbiased. And I'm going to ask the individual who answers at the other end to say, how many phone lines do you have? And they'll say, I have one, or I have three, right? I have one for the kids, one for the fax. And so you make this survey, right? So how would you go about it? Choose phone numbers at random, and how many landlines do you have, and get a sample and plot a histogram. And is that a good way to figure out what the distribution is? And the answer is no, because no one ever picks up the phone and says, I have no phone lines at this house. You've reached a house that has no phone. So clearly that's biased, and it's biased in a very particular way, which is you have 3 times the likelihood of calling a household that has 3 phones as you do calling 1 phone. And likewise, if you want to know family size, and you say, how many brothers and sisters did you have? No one ever says my parents had no children, right? So clearly this is not a good way to take a sample, right? Okay, but this is what's called size biasing, and it can be applied to any non-negative distribution with finite non-zero mean. So if you had a distribution mu, right? So here's my distribution mu. And then what I do is I just multiply by x. So this bias makes the makes that value x times more likely than it was before. This doesn't give me a probability measure, so it's got to divide by the mean, right? So this is size biasing. And you can just apply that and get a new distribution. Also, this can be characterized through a functional equation, which sometimes is more convenient, right? So you can just rewrite this Radon-Nikodym derivative in terms of dual form, in terms of the functions, expectation x f of x. So you kind of flip the signs here, right? So the x comes from here and the m goes on the other side. So it's really the same equation tested by functions, right? Expectation x f of x is kind of factors, right? Expectation x times the expectation, not quite of f of x, but of f of x size biased. Okay, so here you can see that you can kind of be recovered except for that mass at 0. Okay, so this is size biasing, right? It's classic, well-known, right? Oil exploration, right? You'll find the larger oil reserve first if you're just drilling down at random, right? So you're also taking size bias in the context. Just parenthetical, it can also be used for your advantage. If you take a simple random sample of, say, fixed pairs, deterministic pairs, and you want to know the average y divided by the average x, maybe there was like overbilling, the phone company overbilled, you want to know what proportion, so they want to see how much they billed you and how much they should have billed you, and so you want an unbiased estimate of this ratio, and it seems like, well, if we're going to take a simple random sample of pairs and then just form the average y and divide by the average x, that should be a pretty good estimate of the ratio, but it's not. It's a biased estimate of the the true average y over average x. And you can fix this by size biasing. So here it kind of has the opposite effect. This is known as Mizuno's procedure, and you pick the first pair according to size biasing, and then the rest of the pairs uniformly from what remains. So anyway, there's a lot of uses for size biasing in this particular world. And the question is, why does this work? And I'm going to leave this as an exercise for you. Okay, so this is a way you can get an unbiased ratio estimator. Also, size bias makes a large number of other, perhaps unexpected appearances, waiting time paradoxes, tightness, Paul measures, analysis of the log normal distributions, score HUD embedding, distributional approximation, concentration of measure number theory, and today we'll talk about one of the final ones, and infinite divisibility. All these topics and more, doing an advertisement, are covered in the following paper by myself, Richard Aradia, Fred Kaufman, 2009 Probability Surveys article, which has all these examples in there about the wonders of size biasing. Okay, so one of the interesting things and one of the main reasons it's so useful is it has a very interesting particular property when you're talking about sums of variables. Here, we're going to specialize to sums of independent variables, but it's more general than this, but let's talk about it. And we'll basically stick to the independent case today, but this principle is general. So take x1 through xn independent, non-negative random variables. Let's suppose they'll have non-zero finite mean and take the sum. And you might want to know, how does the size bias of the sum relate to the original sum? And it has this kind of magical, I'll call change one property. So you can get a size bias version of W by just making a kind of small, very small perturbation of your sum W, which is pick a random index, okay, that is a random summand from 1 through n, and choose the index independently of all the variables already existing in that sum. Choose it proportional to the mean. Okay, so you're going to have a larger probability of choosing variables with larger mean. Okay, then all you do is you kick that variable out. Right, so maybe you picked, I as that variable, throw that out and replace that variable with a size bias version of itself, which is independent of all the remaining variables in the sum. It doesn't have to be independent of what you threw out, but it does have to be independent of the remaining of the sum once you subtract that variable. So you've just changed one variable, and now you have size bias the entire sum. Okay, so it's kind of interesting property, and it's very, very easy to prove. And even when you go through the 5-line proof, you may still find it a bit unintuitive, but this is the case. Okay, so this will come up again and again, I think, is the main principle. Okay, so this would be this magic change one property. Okay, we'll get back to that. So one interesting thing about transformations is that they may have fixed points, and we may be able to study the fixed points of transformations, right? Fixed points of the transformations, or their fixed points through the fact that they study the fixed points through the fact that they are fixed. They have that property. So let's try to see if there's some fixed point of the size bias. Is there any distribution which is left unchanged? That is, what if it doesn't come out to be very differently than you started with? And you look at the equation, and you can easily see that the only fixed point is kind of this trivial fixed point, which is just point mass, right? So if you take a point mass at a number m, then yes, it doesn't change when you size bias it, right? Okay, and that's it. So maybe we didn't do something interesting enough. So the size bias, by the way, you can also take a minute to work on the back of an envelope to show that the size bias of x is always stochastically larger than x, right? So you really shouldn't expect there to be a non-trivial fixed point to that, because it should always make it somewhat bigger. So since the size bias makes it somewhat bigger, why don't we do a two-step transformation by size biasing and then making it smaller, right? So if we make it bigger by size biasing and then we subtract 1, let's say, then maybe we have a chance of having a fixed point, right? So I don't know if anyone knows what the fixed point is. It does have a fixed point, right? So size bias and subtract 1, and there's a distribution which has that transformation as its fixed point, and it is the Poisson. Okay, so a well-known Poisson distribution has that property. Okay. And then you can prove it very easily just using the identity. And, you don't have to go through it, but or with moments, right? So you can just look at the transformation. You want to say it's on both sides, right? So here you're saying it's a fixed point. So just look at the left-hand side, the right-hand side, and just start plugging in different versions of f's that you like indicator functions or power functions. You'll find easily that this is a unique fixed point. Okay. Okay, now let's think of other ways we can construct transformations with fixed points. And this is the Stein identity, right? So let's look at this. So we've got the Stein identity for the mean zero normal distribution. 72 or earlier, I think. So it's got the same sort of left-hand side. We have this expectation x, f of x also show up for the signs bias, and for the Stein identity, as opposed to the identity that we saw for the size bias, the right-hand side now has a derivative. Okay, so let's let t be the variance of the normal, and Stein showed that the normal 0t is characterized by the fact that this identity holds the expectation of z f of z is t, the variance, times the expectation of the derivative. If that is true for all sufficiently smooth integrable f, this is true if and only if we have a normal distribution. Okay, so this is kind of a nice computational tool you can use to study the normal distribution. Right, so this is what I said, that this holds uniquely specifies the center normal distribution with variance t. Okay, so now we can kind of study, we do study or think of this as a way to measure discrepancy from normality, use the identity, use the amount by which a random variable fails to satisfy this identity as a measure of how far the distribution is from the normal. Right, so this is, I think, the idea that Stein had put in some kind of words. So we can have a distribution, if it's close to satisfying this identity, then it should be close to being normal. And this is a strategy which has worked well to proving very sharp estimates for finite sample normal approximation. Okay, so how do we make some kind of a transformation out of this, right? Is there some way that we could modify this identity to apply to non-Gaussian? Okay, we have to modify it somehow because this identity characterizes the Gaussian, right? So we have to change something, change the left-hand side, change the right-hand side. There's various ways you can do it. So I'll just show you, I guess, my favorite way, how you can modify it, which is, let's see if you take a non-constant mean zero square integrable random variable, does there exist a distribution mu star? So you start having it with a distribution mu. Does there exist a distribution mu star such that it satisfied the identity when I replace x by x star? So we know the answer is yes for Gaussian, right? For Gaussian, x star is x, right? But does it work for anything else? And everything else would have to be different, right? Because the Gaussian is the one that satisfies the uniquely, and the answer is yes. So any mean zero finite second moment random variable has such a x star. So it always exists. And one way that you can get it is also this biasing. So this is like a square biasing now. So this is the non-negative. So this is a size bias is for non-negative random variables. Here it's mean zero, so it takes on positive and negative values. Strangely, you can't size bias it, but you can double size bias it, right? You can't size bias it because x will be negative, but x squared is always positive, so you can double size bias it. So here we double size bias it, or we could say we square size bias it, okay? That makes it bigger, right? And then you multiply by the uniform, and that makes it smaller, okay? So it has a chance of having a fixed point. Indeed, it does have a fixed point, and the fixed point is the normal, as we know from the Stein identity, right? So this is called the zero bias, so named because it's like size biasing mean zero random variable.
T is the second moment.
Yeah. T is, yes, the variance. Yes, like in the last slide. Yeah.
Variance or second one?
I'm sorry.
Variance or mean zero?
It's mean zero. Yeah. So it's the same. Yeah.
So if we consider kind of Stein equation for the Poisson, is any connection to the previous kind of fixed point?
Not directly.
Not directly.
Yeah. They're sort of different. Yeah. So there's I'll show you some more. They look kind of the same for various distributions, but there's no, I don't think there's any direct way to connect one to the other. Okay, so here are some we've seen now two transformations with distributional fixed points. So you have X non-negative, finite non-zero mean, size bias, subtract one, right? You've got mean zero, finite variance, double size bias multiplied by a uniform. Let's just throw out a few others, right? Make it big and then make it small would be kind of a scheme to see. So make it big by size biasing, make it small by multiplying by a uniform. Okay, maybe that is a fixed point. How about make it bigger by adding one, make it smaller by multiplying by a uniform, right? So all these transformations do have unique fixed points, right? So the first we know is the Poisson and the second we know is the normal. What about these two? Anyone recognize them? So one of them is a distribution which for sure you've heard of. The third one, and one of them is a distribution you probably have never heard of, even though these are very kind of close, right? I mean, it's hard to know. So the very, very familiar distribution is a distribution called the exponential distribution, which you've heard of. And the fourth one is a distribution called the Dickman distribution, which occurs in number theory, which probably no one's ever heard of unless you've heard of it from me. Or from Richard. Richard was first in spreading the word on the Dickman distribution. Okay, so these are I would say, way beyond the, so I guess the message here is that they apply these ideas about studying distributions by fixed point properties is because you can apply well beyond the normal, just to give you some broad range of examples, and there are many, many more. Okay, so what are the properties of the zero bias? Again, we know that it always exists for positive finite variance. It's kind of homogeneous. You can multiply by a constant before or after you. Zero bias has continuity properties. The distribution is always absolutely continuous. It kind of fills in the gaps between, a distribution that you start with and support property. But the most interesting property is that it has also this change one property, right? So it's the same, right? Up to what you pick by and what you replace by. But just like the size bias, if you have independent mean zero random variables and their finite non-zero variance, then pick one proportional now to its variance and just kick that one out and replace it with its zero bias version. And that zero bias is the sum. Okay, so I think this gives you kind of a trivial way to think about the central limit theorem as a triviality, right? Which is if you have a sum of a large number of variables, then when you zero bias it, it hardly changes at all, right? Because you changed one variable. So that means it's nearly a fixed point of this transformation, which means that it must be nearly Gaussian because the Gaussian is the unique fixed point, right? So it gives you an intuitive reason why the central limit theorem is true. And in fact, you can make that quite precise using the Goldstein method, but this is, I would say, an intuitive way to see that the central limit theorem holds. Okay, so here also has a surprising connection, or surprising connection to infinite divisibility. Let's recall the distribution is classically infinitely divisible if for any n you could find an nth root, right? So that is, you take distribution and you say it's got some n distribution, and when you take the sum n distribution and you add n of those together, x1n up to xn, those are all IID, then you recover x, right? So this is called infinite divisibility. And now Steudel in 1970 showed that if you have a finite non-zero mean random variable x that is infinitely divisible if and only if its size bias is equal to the distribution to the original random variable plus an independent increment. Okay, interesting. Okay, so for example, we already know that the Poisson, right, it's the fixed point of this size bias plus one. So the size bias is x plus one. And since one is independent of everything, this is a short proof that the Poisson is infinitely divisible because the one is independent, right? Okay. So now with my collaborator Uwe Schmuck, we thought, well, what about, this is size bias, and maybe we could do something with second moments. We can extend the zero bias just by subtracting the mean, size biasing, and adding the mean. Okay, so we get the following result, which is quite similar, right? Which is that an L2 random variable X is infinitely divisible if and only if there exist random variables, uniform 0, 1, and a Y, all independent, such that when you zero bias it, you get X plus an independent increment. So that's the same, only we just, really it's just this like Streudel's result. So it's just X plus, so we know, if you think back to what the size, what the zero bias was, it was square biasing and multiplying by a uniform. So this is like this, something got square biased and then something got multiplied by a uniform. Okay, so this is well, it's sort of well known when an L2 mean zero, say random variable is infinitely divisible by Kolmogorov formulation. So there's some previous work that used probabilistic methods to prove slightly weaker results about equivalence of what Kolmogorov said. So Kolmogorov is going to solve the problem by saying, well, wait a minute, we already know the answer to when an L2 random variable is infinitely divisible, which is if its cumulative generating function has this form, right? So you can look at this cumulative generating function, right? It's the log of the moment generating function, log of the characteristic function, and he says that this is the if and only if it is true. So what did our explanation add to this? Well, there's this Levy measure here, right? What's this called? This new is the Levy measure. This is kind of the Gaussian component. When you exponentiate this, right? If you have point mass at 0, right, then all this goes away because you're integrating away from 0. So if you have point mass at 0, then it's e to the minus sigma squared over 2 times chi squared. So this is just the characteristic function of a Gaussian. And then he said, well, then there's also this other piece, right, that you get here. But what I showed with my colleague was that this Levy measure in Kolmogorov's theorem is actually the distribution of Y. So this gives this Levy measure in Kolmogorov's theorem a probabilistic interpretation. Right? What this Levy-Khinchin measure is in Kolmogorov's theorem. And our characterization is equivalent to Kolmogorov's theorem, right? So you can have Kolmogorov, you can prove if and only if you, from what we have, you can prove if and only if you get Kolmogorov's theorem, so it's absolutely equivalent. So I guess every talk they say should have one proof. So here's a little proof, okay, of how we get one direction. So suppose we start with an infinitely divisible distribution, means zero finite variance. So that means that we can write it out, as I said, we can write it out as the sum of n IID roots, let's say. And then you zero bias. Sometimes they say size bias, I mean zero bias, so excuse me if I make that mistake. So you zero bias, and when you zero bias, it means you threw one of them out. It doesn't matter which one you threw out, because they're all identically distributed, right? So you can just, they're all exchangeable, throw one out and add x and n. And so when you zero bias it, you get, this got thrown out, and then you added this in. So you threw this out, and then the zero bias is the uniform times the square bias, and it'll take the limit, and then you're done. So that's really, it says that if it's infinitely divisible, right, then it's, because the left-hand side doesn't depend on n, right? So I can take the limit and I still maintain the equality with the left-hand side, right? So this is 2 lines, and you see that the result looks trivial, and I agree it's trivial, completely trivial, but since it's equivalent to Kolmogorov's theorem, it proves Kolmogorov's theorem is true. Okay, so that's really the end of the road for the classical, right? So now there's this whole field called free probability, right? And to me, it's a fascinating area, and it's if you work in probability, then it's like going into a carnival funhouse where there's mirrors, where that make you look fat or small or wide, right? And it's like you look familiar, things look familiar, but they're not the same, right? And things you think you understand when you go in this carnival funhouse, there's something weird, different about them, and all your intuition basically collapses. Let's just say. Okay, so the idea of these distributional transforms, they work well, in this classical world. So the big question that I've had for a while is, can we use any of these ideas in free probability? And I think the first question we need to answer is, what is this free probability? So I think it's unusual. It's an unknown, right, area was to me. I don't know if there's anyone here who's an expert. I hope so that you can correct me if I say anything wrong. So if you don't know anything about free probability, you're in luck, because I've got a 2-slide crash course. It's gonna explain, well, just enough what we need. Okay, free probability. Okay, so here's the first slide of a 2-slide crash course in free probability. Let's start with just matrices. Say you have a K by K Hermitian matrix A, let's call it little a, and you've got its moment, kind of a moment sequence. Looks like a moment, like you revealed you have a sequence. So the trace with a bar, this is the standard normalized trace, which is I'm going to take the trace and divide by K. Okay. So let's take the normalized trace of the powers of my matrix A, right? And this turns out to be a moment sequence of a probability measure. Okay. That's interesting, but we already kind of know that, because we could just, if it's a Hermitian matrix, we can just use the spectral decomposition, right? So if you use the spectral decomposition, an A star lambda mu, or mu is a orthogonal matrix and lambda is a diagonal matrix. So you just use the spectral decomposition, right? And you replace your A with u star lambda u, take to the nth power, and the mu stars and mu's cancel, and then use the the rotation variance of the trace. You get the trace. It's the same as the standardized trace of lambda to the n. So that's just 1 over k, because that's the standardized trace, and the trace is just the eigenvalues raised to the nth power, right? So that's the measure, which is the empirical measure of the eigenvalues, right? So here we have the empirical spectral distribution of that. So this Hermitian K by K matrix is in this way associated to a probability measure. Okay, and now we can ask, let's extract the minimal ingredients, like you need something like a trace, you need something like an adjoint, et cetera, and apply this to spaces of linear operators. That's slide 1 of what it means to be in free probability, right? Which we work with these linear operators on spaces on which we've endowed enough structure so that this kind of argument applies, such that every one of these operators, we can associate a probability measure in the same way we can associate a probability measure with a K by K Hermitian matrix. Halfway through the course. Okay, so, well, if it's going to be like probability, then there's got to be something like independence, right? So what's independence? So in regular classical probability, we've got independence of sigma algebras. Here we have subalgebras, algebraic structures, right? So we say the subalgebras A1 through AK are freely independent. This is kind of maybe a little readable. So we've got if the so here I'm doing something a little sloppy, which I'm going to say every one of these elements of the algebra A is associated with a probability measure, right? So what I have then, I'm going to take expectation with respect to that probability measure. Okay, so that's where this expectation appears, right? The expectation appears because this A is associated with a probability measure. Okay, so that's what I'm doing. Okay, so now we take a string of these elements. Each one of those have expectation 0, and they're coming from these different algebras, right? So like I1 is from one of them, but the one next to it is from a different one. Right? So we're imposing the condition that if it's to the right or if it's to your right or to your left, it's from a different algebra. Okay? And these are freely independent when this product is 0 every time for all ways we can do that. So that kind of looks familiar, right? It's like the expectation of the product is the product of the expectations, right? Okay, so that's the idea of free independence. So for example, simple example, if we've got A from algebra A1 and B from algebra A2, and those are freely independent, then this expectation AB is 0, right? Because nothing is adjacent to something which is in the same algebra. Okay, so that's the idea of free independence. Okay, and this, you can see right away, this is quite different from what happens in this commutative random variable world, because if these variables commuted, you've got expectation A squared, expectation B squared, which in general is going to be non-zero, right? So right away you see that there's difference. Okay. So a few more things to go over before we move on. Oops. Okay. So in the classical world, we've got the Fourier transform and the limit generating function, characteristic function, and this cumulative function. So here, those transforms are replaced by Cauchy transform and the R transform. These are a little less intuitive. So the role of the Fourier transform in free probability is now played by the Cauchy transform. This is just what works out to be natural. Okay, so the Cauchy transform is this form 1 over z minus x. Z is in the upper half plane. This way, this expectation always exists because x is real. So this always has an imaginary, positive imaginary component. So it can never be 0, right? So this always exists. And then the cumulative generating function, right, in the classical world is you just take the logarithm. No such luck here. Okay, so here you solve this kind of inverse equation. So the cumulative generating function is this function R, which satisfies this identity in some neighborhood, maybe not everywhere. Okay, all right. And the cumulants that it counts in this generating function are these cumulants for intersecting partitions, or non-overlapping partitions of products, but we won't go into that. Okay, so let's see, what else do we need to know? So there's also, this intriguing free central limit theorem, which is analogous to our very familiar classical central limit theorem. So you can read this as the free central limit theorem, the classical central limit theorem. So if x1 and xn are independent or freely independent, identically distributed, and have mean 0 finite variance, then their standardized sum converges to, if you're in the free world and those are freely independent, it converges to the semicircle distribution. And if you're in the classical world, it converges to the Gaussian distribution. So the semicircle distribution plays the role of the Gaussian distribution in this free probability world, right? And the semicircle distribution is the distribution of this, the distribution of random matrices, right? For Hermitian, for random Hermitian random matrices, right? That have independent components along the diagonal, above the diagonal, right? Then as the dimension grows, then their eigenvalue, just the empirical eigenvalue distribution converges to the semicircle distribution. Okay, so that's kind of, yeah.
Why you think it's called free?
Why free? Because it's called free because the elements of the algebra obey no algebraic relation. They're free. So like they're free of any algebraic relations among them. Okay, so they don't satisfy like anything like a squared b equals c. They're free of they're free to do whatever they want. You're not constrained. That's the right why it's free.
And this has nothing to do with that. What's that? The fuzzy probability. It's completely different.
Nothing to do with that. Yeah. Okay, so this is the end of your 2-slide crash course. Okay, so now you're to the expert level. Okay, so what do we want to do here? So the probabilist who's been paying attention, I guess, is cut off at the bottom. The surprise free probability, there's nothing random here. So all these, so there's we started with a nice Hermitian matrix, right? It wasn't a random matrix, but it's associated with the probability distribution, right? When we go to this land of operators, we still didn't introduce anything random, right? These are probability measures that came from the spectral distribution of these operators, right? So there's free probability, but there's no randomness. You can interject it, but there's no randomness. Okay, so one of the ingredients, there's a few things that really change when you go into this world, right? Because of the non-commutativity. So there's this free difference quotient. Okay, so suppose you just wanted to do something really simple, like differentiate, lambda cubed, but you want to do this, right, in the non-commutative world, and we have Frechet, you want to calculate, say, directional derivative and the hope of Frechet derivative exists. So, so we've got derivative at A in the direction of H, right? So it's a space, right? So these are operators, right? Some high dimensional operator, infinite dimensional operators. So we have some A operator. We're going to take the derivative of this nice simple cubic function, but in the direction of some H. And the way you do that is you go out on the line between A and H, and you take the derivative, this one-dimensional variable T, right? This is this classic way you get a directional derivative. Okay, so in this case, it's just the cube, right? And so you just replace this function, by its cube, and so you write it out like this, and then things don't commute, right? So you're going to get HAA, AHA, AH plus other. That's so you get the A cubed, right? The interesting term, right, which is of order T, is this one, and then things which are going to be of smaller order. Okay, and then you take the derivative, and as T goes to 0, right? Then you get this form as the derivative, right? This is this non-commutative derivative. And then you can write this out in this kind of funny way, which is like this, and this hash means put the H in the middle and multiply all these things together. Basically, what I want to have you to take away from this, so I guess the screen isn't showing everything, but what's down here is that we're going to have this this free difference quotient. It's going to be a function of two variables. So it's going to be p lambda minus p mu lambda minus mu, because that's what this is, right? Lambda cubed minus mu cubed over lambda minus mu is this lambda squared plus lambda mu plus mu squared, right? So this is the free difference quotient that's going to show up in a minute. Okay, and this is where it comes from. All right, so now let's go back, and we're looking to see, does this zero bias transformation, which worked so nicely in the classical world, does it exist in the free world? And so now we've got, since we know something about, so this free difference quotient, we have some guess as to what we might do here with the classical Stein equation, right? So here the classical Stein equation has a derivative, and we know that the derivatives look like these free difference quotients, right? And this is kind of well known, right, in the free probability world, that the derivatives are played by these difference quotients. So our guess, right, natural guess for the free version of this Stein identity is, and we're going to write it in kind of a sloppy way. It's really a function of two variables, right? So this is the putative value of the free zero bias of X. We'll write as X circ, semicircle, right? But really it's a function of these two variables where these are going to be independent copies of each other. So this is what the guess would be, because the derivative gets replaced by the difference quotient. Okay, so that's what we think the free zero bias should be. And when we look at that, we ask, can we prove this exists? Is it true, like it is in the classical case, that for every mean zero finite variance X, that there exists such a distribution? And does it have the right fixed point property, right? Okay, so the answer is yes. It always exists, and it has the right fixed point property. So the way you show it exists, and the functions that work well, because we talk about Cauchy transforms, and those are kind of the expectations of these kinds of functions, right? Z minus X, those are called resolvent functions. And we take the difference quotient of resolvent functions, then sort of magical things happen. So the right-hand side of the equation, where we have the difference quotient of the resolvent function, this is the one at X, the one at Y, divided by the difference, it becomes the product. And then on the right-hand side, that gives me expectation of the product of independent random variables, and therefore we get expectation of the square, and we write this out in terms of the Cauchy transform, and it gives us an algebraic equation for the Cauchy transform of the putative random variable, which is the free zero bias of X. Okay, so there's a lot of complex analysis here, which is kind of ironic for someone who went into Stein method to avoid characteristic functions. But you have to deal with.
But the middle one, the last one, the square is outside or inside?
This is the square.
No, on the top.
Here? Yeah, that's because you got F, and this is the X and the Y this X gets replaced by X circ and this Y gets replaced by Y circ, but they're independent. So you get this, oh no, it's
Outside.
on the outside.
Yeah, okay.
Thank you. Good catch, outside, right, outside. Thank you. Yeah, right, and then you get the, thank you. Okay. All right, so anyway, so there's two properties you need to verify. The function is a Cauchy transform and you verify them, and therefore it's a Cauchy transform, and this exists. That is, you can take a square root. And then you can ask, does it have a nice fixed point? What fixed point should it have? And the fixed point it should have would be the semicircle law. So you can take a sequence of powers and you plug those in, and indeed you get the Catalan numbers, which are the moments of the semicircle law. So this transformation looks like it's the right thing. Okay, so during the course of the work, we had to make some other kind of extensions or discoveries, and one was this weird thing. We just need a special case of this. We still don't know what to make of what this is, but we only use one special case, which I'll show you, which is if you, in some cases, the square root or the geometric mean of Cauchy transforms is again a Cauchy transform. So this wasn't known. And so they have it's a weird condition under which it works, but if you have this condition, then you can take the geometric mean of two Cauchy transforms. We sort of only care about it in the case where there's some nice properties of this kind of 2-to-1 transformation, but the hypothesis of the lemma are always met if y is 0. So if y is 0, then this right-hand side is going to be 0, and 0 is less than or equal to 0. So you can't see it down here. So this is G of, there was already a sharp taken. So this was supposed to be like a flat. So this is 1 over Z x of Z. So this is just the Cauchy transform of the point mass at 0. So this is the one that we needed to exist, but more of these exist generally. And then we have the analog. So if you remember, so this would be the Cauchy transform of the square bias, right? But it's simple. That's a simple transformation, and you see it has kind of, well, I mean, it's just a generating function where you just shift the moments up by 2, etc. But this identity in the classical world translates to this identity in the free world. So in the classical world, remember that we take the 0 bias by square biasing and then multiply by a uniform, right? So we made it bigger, then made it smaller. And this one is working kind of similarly. In fact, the first step's the same. You take the square bias and then you take the flat transformation. The flat transformation is some kind of a weird interpolation, like a Cauchy transform type interpolation with point mass at 0. So it's making it smaller in some sense. We still don't understand this transformation very well or much. But anyway, this is the analog of the classical way we construct the 0 bias. And in this way, with this flat transformation, you could define it more generally, even if it's not mean 0, but it agrees with what it's supposed to be when the mean is 0. Okay, so now we have a few more minutes, so I'll show you what else I've got briefly. So we have similar regularity properties. You might remember the slide of the regularity properties that we had for the classical 0 bias, that it exists, it's homogeneous, that it's kind of continuous. And then there was also the property, the magic property that of the change 1 property. And we're pretty sure this doesn't hold. Okay, we actually don't yet know, but everything points to the fact that the change 1 property, which made everything work so nicely in the classical world, doesn't hold here. But there is some kind of an analog which we are sure does hold. And I don't have much time to go through it. So let me just say this is the property. So one thing, or give a little detail, one thing that goes, I think, terribly much differently than it does in the classical world is conditioning. So if you condition on you've got some function of x plus y and you condition on x, then the right-hand side should depend on, that is, you average over y, right? So it should depend on x. So we're used to having conditioning where we're gonna just, if these are independent, we're just gonna integrate this over y, right? In the free world, the right-hand side, so this is, we're gonna take the conditional expectation of 1 over z minus x. So maybe we expect something like 1 over something minus x, but the something we get still depends on the distribution of y. So X is distribution mu and Y is distribution nu. And for some weird reason, this is a result of beyond. This conditioning retains the distribution of Y even though you've conditioned on it. Okay, so this is what causes a lot of problems, yes, or what makes it interesting, let's say. We did find analog of the change one property in terms of Cauchy transforms. To compare, if you write down what the change one property is in the classical world in terms of Fourier transforms, right, then this would be the Fourier transform of the zero bias, and this is, you just took one out, right? So this is the product because they're independent. You took one out of the sum. That's the Fourier transform of what's left. You took one out of the sum, and then you replaced one, and this is the Fourier transform of the one you put back. So here you see the replace one property, and it's kind of similar here, right? So this is all that happened here was this is still the x1. This one x1 looks like that x1. This w minus x1 looks like that w minus x1, and you just changed x1, right? So you just made that one into a star. But it's much more complicated in that it's a composition, but this seems to be the analog of what the change one property is for the free zero bias. Okay, and what can we prove with this? And we can prove the analogous result that we had in the classical world regarding free infinite divisibility, right? So it's infinite divisibility is exactly the same, but the addition is defined by this free addition, right? Which is where you take the sum of the R transforms. It's what linearizes the cumulants, basically. Okay, so this is the free sum. So you define a free sum in sort of a natural way, right? Like you would say, if you have independence, it makes the Fourier transform, is the product of the sum ends, right? Or that the cumulant function adds when you take the log. So the free sum is what makes the cumulant functions add, is one way to say this. So there's a paper way back in 1992-93, where Brukhovic and Voshulescu characterized freely infinitely divisible distributions in terms of their R transform. So it's all very, it's all very complex analytic. They say this function has to be holomorphic in the entire upper half plane. And also there was a kind of Levy-Kinchin formula known for an expansion of this Voshulescu transform. It looks kind of like the one in the classical case. You have something multiplied by a Levy measure. So we were able to add to this a little bit, and we have the result that says that yes, it's true. We have an independent proof which gives a new identity in terms of Cauchy transforms, right? So we have that it's freely infinitely divisible. This, of course, is under the L2 condition. So this identity was not known. There's a identity in terms of how the Cauchy transforms behave. And this identity holds if and only if this previous result that was known in the 92 paper holds, right? So we have an independent proof that introduces a new identity. And furthermore, the same effect as in the classical case, we were able to identify what this Levy measure is, which hadn't been identified before, which is it's the distribution of this Y, kind of in the same way that it was identified in the classical case, right? If you call that probabilistic. Okay, so this is, in a sense, the free version of this other result that I joined with Uwe Schmuck about this gives the kind of a meaning to what the Levy measure is. Here again, we see the same kind of effect. All right, so I'll just stop here with some pre-associations, right? So this proof we have of this free Levy-Kinchin formula, as I said, is new and it's equivalent. Cauchy transform identity is equivalent to what was known, but gives probabilistic meaning, as I've said. So we want to see if we could use this new identity because it should be able to be applied, where you have this R transform is harder to get than the G transform, as you saw. R transform is kind of the inverse of the Cauchy transform. So maybe this gives us a better chance of proving things about infinite divisibility using the more easily available transform. And to confess, our goal really was to study the free central limit theorem with this transform, right? So we haven't yet been successful on that, but we at least made progress by showing the transform exists. So we're going to hope to get back to that and maybe say something about approximations in that and apply that in apply that into the world of random matrix theory. Okay, so that's it. Thank you. Yeah.
question? Do you have a free version of size biasing?
So we don't, well,